Every single day, more than 20 million banknotes are destroyed in the United States. That is a mountain of money that could reach the sky. But what exactly happens to them? Are they burned, shredded, or maybe turned into something completely unexpected? US dollars have their own life cycle, and their disposal is a high-security operation involving armored trucks, strict inspections, and secret routes. How do old banknotes disappear forever? And is there any way to save them? Let's find out. The dollar as a currency has a fascinating history. It all began in the mid-17th century. The first dollars appeared in the New England colonies in the year 1690, at a time when the United States did not yet have a unified national currency. Back then, the colonies issued their own money, and one of these was the so-called paper dollar. However, the true dollar as we know it today emerged later, in the year 1792, when the United States Congress passed the Coinage Act. This was the country's first attempt to introduce a single currency, establishing the dollar standard based on a silver coin. The dollar quickly became the main currency for trade and wealth accumulation, as the nation sought to create a stable and accessible monetary system that would support its economy and commercial ties. Today, the dollar has evolved into one of the world's leading currencies, used in international transactions across the globe. The idea of disposing of old banknotes arose at the beginning of modern financial systems, especially when currencies started to become standardized and central banks began managing the money supply. In other words, the process of removing worn-out dollars started as soon as money became a stable and regulated instrument, though it was not officially systematized until much later. The concept of destroying damaged money first appeared in Great Britain during the 19th century, when the British government realized that allowing worn-out banknotes or coins to remain in circulation reduced the overall value of the currency. However, the systematic destruction of money, as it is done today, only became possible with advancements in modern financial systems and technology. In the United States, the first efforts to manage old and worn-out dollars began in the mid-19th century, when the first central authorities responsible for currency emerged, and money became a key instrument of the national economy. In the year 1861, when the United States first introduced federal paper money, known as greenbacks, the need arose to organize their circulation, including their disposal. The official process of destroying old dollars was established by the Federal Reserve after its creation in the year 1913. The Federal Reserve became the primary institution responsible for regulating the money supply, including removing old banknotes from circulation. The idea of destroying old banknotes was first introduced by central banks, which discovered that worn-out and damaged money not only harmed the image of a national currency, but could also create economic problems. If old banknotes remained in circulation, it could destabilize the monetary system, increase the risk of counterfeiting, and even affect inflation rates. To prevent this, the Federal Reserve established a clear policy outlining when and how banknotes should be removed from circulation. This became an essential part of maintaining economic stability. So, what exactly happens to all the money that can no longer be used and that no one wants to see anymore? Are they just burned? Well, not exactly. Disposing of US dollars is a complex process that follows a highly regulated system, ensuring both destruction and security. Here's how it works. First of all, when money is removed from circulation, whether it is declared damaged or obsolete, it does not simply get thrown in the trash. Everything goes through the United States Federal Reserve System, which manages the issuance and renewal of dollars. They collect old banknotes and send them to specialized facilities for further disposal. When you or someone else brings damaged or worn-out dollars to a bank, that is where the process begins. Banks have strict procedures for identifying banknotes that are no longer fit for circulation. These banknotes are inspected both manually and automatically using specialized machines that detect damage, wear, or counterfeit signs. Modern ATMs and cash dispensers are also equipped with sensors to detect worn-out banknotes. If a bill is found to be damaged or degraded, it is usually placed into special compartments or sent to sorting machines in banks. Once a sufficient number of old banknotes accumulate in banks, they are sent to the next stage, The Federal Reserve. These are special facilities located across the country that inspect, replace, and dispose of currency. Several such centers exist across the United States, strategically positioned to efficiently serve all regions. The process of transporting old banknotes to the Federal Reserve or specialized disposal facilities is strictly regulated. Banks typically work with security firms specializing in transporting large sums of money. Old banknotes are packed into special bags or containers that are sealed and secured against unauthorized access. This is crucial because even old money remains a potential target for theft or counterfeiting if not handled properly. Security guards or specialized couriers deliver these packages to the Federal Reserve or disposal facilities. The transport companies involved in this process operate under the highest security standards, and shipments are often escorted by police or other security services when necessary. You would not believe how many old banknotes accumulate each year, and this applies not only to US dollars, but also to other currencies. Bank vaults are not limitless in space, so from time to time, large batches of worn-out bills must be removed. Every day, thousands of banknotes pass through people's hands. Some get crumpled, some get coffee spilled on them, and some even end up in the laundry. Add the natural wear and tear, and you have a massive pile of money that is no longer usable. Imagine this. Every single day, the United States Federal Reserve destroys millions of banknotes. If you stacked them up, they would reach as high as a skyscraper. And that is just in one day. Transporting such massive amounts requires trucks. Money is packed into special bags or boxes. Each container has a unique number and seal to ensure it remains unopened. And while these may no longer be real money in a traditional sense, they still hold value. So the security of such shipments is incredibly tight. It is almost like a scene from an action movie. Armored trucks, armed guards, secret routes. Except here, instead of a heist, the mission is to get rid of this money forever. A true financial thriller, right? Before the old banknotes are destroyed, they go through careful inspection. Special systems determine whether they can be reused. If a banknote still retains at least 50% of its original form, it can be reintroduced into circulation after a special treatment, such as reprocessing or trimming. This significantly reduces the cost of printing new banknotes. Every year, an enormous amount of old dollars is destroyed in the United States. For example, in the year 2020, around 7 billion banknotes were eliminated because they were too worn out to remain in circulation. This process is continuously maintained at the highest level to keep the currency stable. Some damaged banknotes are not immediately burned. Instead, they are recycled into other materials, such as fibers that are later used to produce new banknotes. This helps reduce production costs and support sustainability efforts. There is also an interesting psychological aspect to this process. For many people, destroying money might seem like a loss of value, but in reality, it is part of a continuous cycle that helps preserve the stability and worth of the currency. That is why this process is just as crucial as printing new money. Old US dollars are often destroyed in specialized incinerators or through processes that ensure maximum material utilization. Banknotes are burned at temperatures of approximately 2,000 degrees Fahrenheit, completely obliterating them. Furthermore, advanced filtration and technology capture toxic gases and other harmful byproducts to ensure safety during the process. But does it not feel strange to burn so much money? Given how much we spend daily, these sums seem enormous. However, the portion of money that gets destroyed is actually a tiny fraction of the total circulating supply. In the end, the system is highly reliable and efficient. After the banknotes are burned, tons of ash remain. Some companies repurpose this ash into materials for making compost or even bricks. This part fascinates me. Dollars get reborn and continue serving humanity in new ways. Imagine a motor that can spin up to 23,000 revolutions per minute and produce a level of power that in the past only Formula 1 race cars could achieve. Now picture that motor installed in your Tesla. How did Tesla manage to create such revolutionary electric motors that have made its cars the fastest in the world? From asynchronous motors to the innovative plaid carbon-wrapped versions, today we will dive into the world of technology that is reshaping the automotive industry forever. Are you ready to discover what is inside the most powerful electric motors of our time? Then let us get going. Asynchronous or induction motors were installed on Tesla Model S and Tesla Model X in their earlier versions. Synchronous motors with permanent magnets are used in Tesla Model 3, Tesla Model Y, and later versions of Model S and Model X. Wound rotor motors represent an enhanced technology that combines the benefits of the previous types. Each of these motors has its own unique aspects in manufacturing. Before initiating production, Tesla engineers design the motor using modern modeling software. The design process considers the materials for magnets and windings, the shape of the rotor and stator for maximum efficiency, the cooling system to prevent overheating, the balance of weight, and the positioning of the motor in the car. After completing digital modeling, prototypes are produced and tested under laboratory conditions. Now let us move on to the stage that focuses on the key components. The first component is the stator. It is the heart of the electric motor and the stationary part of the motor, containing copper wire windings. The stator core is made of many thin layers of electrical steel, which helps reduce energy losses from eddy currents. These steel sheets are cut by laser cutting or stamping. The sheets are assembled together and pressed into the form of the stator. The next step is the coil winding process. Automated winding is utilized, along with a precise calculation of the number of turns. In order to boost efficiency, hollow copper wires with coolant flowing inside are used. After the winding, vacuum impregnation with varnish takes place to protect the windings from overheating and damage. We then proceed to the stator assembly stage. The windings are connected to electrical contacts. Temperature sensors are installed to monitor heating. The completed stator is subjected to quality control and testing. The rotor is the moving part of the motor. Tesla uses two types of rotors. An asynchronous rotor with a squirrel cage is employed in induction motors. It is made of aluminum or copper by casting the metal into a mold. A rotor with permanent magnets is used in Tesla's synchronous motors. It contains magnets based on rare earth metals, creating a strong magnetic field. As with the stator, a multi-layer steel structure is used for manufacturing the rotor. The steel sheets are cut and either glued or pressed together into the shape of the rotor. Neodymium magnets are inserted into the rotor body. The magnets are secured by adhesive or mechanical fasteners so that they can withstand rotational speeds of up to 20,000 revolutions per minute. Because the rotor spins at high velocity, perfect balancing is essential to avoid vibrations. The rotor is tested on specialized equipment that automatically adds or removes material to adjust the balance. The next stage is motor cooling. Tesla employs liquid cooling for its electric motors. Coolant circulates through channels in the motor housing, carrying away excess heat. This enables the motor to function at high power levels. The rotor is mounted on bearings for minimal friction. The stator and rotor are placed inside the motor housing. All components are connected according to the design. A controller operates the motor by regulating power and rotational speed. Metal oxide semiconductor. Field effect transistors, or insulated gate bipolar transistors, are employed to convert electric current. We now move on to the final step, which involves filling the system with cold fluid. The coolant is introduced into the cooling system and checked carefully for leaks. Following assembly, every motor undergoes an extensive battery of tests. A no-load test verifies smooth rotation. A load test evaluates efficiency and energy consumption. A thermal test stresses the motor under maximum loads. A noise test measures noise and vibration. Only after passing all these tests successfully does the motor proceed to the production of Tesla vehicles. Manufacturing Tesla's electric motors is a high-technology process that integrates advanced engineering approaches, automated manufacturing, and sophisticated testing methods. Tesla continually improves its motors, making them more efficient, more compact, and more powerful. This technology lets Tesla produce electric vehicles that outdo the competition in power, range, and reliability. The story of how Tesla developed electric motors for its cars is one of innovative technology, risk-taking, and the relentless efforts of engineers. It all started with an ambitious plan to revolutionize the automotive industry, and although initially the company did not produce its own motors, it ultimately became a leader in this domain. Tesla Motors was founded in the year 2003 by a group of engineers, which included Martin Eberhard, Mark Tarpenning, Ian Wright, Jeffrey Brian Straubel, and the future chief of the company, Elon Musk. The main vision was to create an entirely electric car capable of competing with conventional gasoline-powered vehicles. At that time, electric vehicles did exist, but they were slow and inefficient. That was when the Tesla team decided to utilize an asynchronous electric motor, originally patented by Nikola Tesla in the year 1888. Tesla's first electric motor was developed using technology from a company named AC Propulsion, which was creating high-powered electric motors for electric car prototypes. Tesla established a licensing deal with AC Propulsion and adapted its technology for its first model, the Tesla Roadster of the year 2008. This was a three-phase asynchronous motor featuring a rotating magnetic field. It was manufactured with an aluminum rotor, which provided excellent efficiency. The maximum output was 248 horsepower, enabling the Roadster to accelerate to 61 miles per hour in 3 9/10 seconds. Despite the success of this first vehicle, Tesla encountered difficulties with component supplies. The motors were made at external factories, and quality control was lacking. This pushed the company to consider setting up its own production lines. Transitioning to in-house production took place from the year 2010 to the year 2012. When Tesla started developing the Tesla Model S, it became clear that the company needed to manufacture its own electric motors. There were multiple reasons for this. The first reason was cost, since sourcing motors from external suppliers was expensive. Tesla also wanted a highly efficient motor designed to meet its specific requirements, meaning the design had to be optimized. Quality control was the third reason, because in-house production allowed the company to oversee every aspect of manufacturing. In the year 2010, Tesla purchased a plant in Fremont, California, previously owned by General Motors and Toyota. This was a pivotal milestone in scaling up production. In the year 2012, the Tesla Model S became the company's first vehicle to use Tesla's in-house electric motor. It was more powerful and more efficient than the previous generation's motors. The Tesla Model S motor of the year 2012 represented a breakthrough in technology. It was created using asynchronous induction motor principles, with a copper rotor instead of the aluminum rotor that was in the Roadster. The copper rotor raised efficiency and diminished heat losses. The performance version delivered 416 horsepower, enabling acceleration to 61 miles per hour in 4 4/10 seconds. This model drew global attention, and Tesla expanded rapidly thereafter. Let us examine the newer generations of motors from the year 2017 to the year 2020. Although asynchronous motors remained efficient, Tesla's engineers began exploring new motor designs. In the year 2017, during the development of Tesla Model 3, the company chose to adopt synchronous motors with permanent magnets. The Tesla Model 3 motor, starting in the year 2017, is a synchronous motor with permanent magnets. This made the motor smaller, lighter, and more efficient. Neodymium magnets helped reduce energy consumption. The refined cooling system enhanced reliability. This motor became standard in Tesla Model 3 and Tesla Model Y. However, Tesla did not stop using asynchronous motors and continued installing them on the front axle of Tesla Model S and Tesla Model X for dual motor versions. Tesla pushed forward and introduced its plaid carbon-wrapped motor technology, which premiered in the year 2021 in Tesla Model S Plaid. Plaid carbon-wrapped motor is a revolutionary solution. It utilizes a carbon wrapping on the rotor, enabling incredibly high speeds of up to 23,000 revolutions per minute. An improved cooling system endures extreme stresses. The Tesla Model S Plaid can accelerate to 61 miles per hour in only 1 99/100 seconds, making it the fastest production electric car in the world. This technology was entirely developed by Tesla's engineering team and is unmatched by any competitors. Manufacturing electric motors for Tesla cars is a sophisticated and advanced process, encompassing pioneering research, modern simulation, automated assembly, and meticulous testing. Tesla gradually evolved from employing asynchronous motors in its early models to integrating state-of-the-art synchronous motors with permanent magnets and the revolutionary plaid carbon-wrapped motor. Through continuous enhancements of its technology, Tesla has produced motors that combine outstanding efficiency, power, and compactness. This enables its electric vehicles to surpass competing models in acceleration, energy consumption, and reliability. Tesla's decision to make electric motors in-house allowed the company to manage quality, reduce costs, and refine designs, proving to be instrumental in its expansion. The unwavering drive toward innovation and the pursuit of new advancements solidify Tesla's role as a leader in electric transportation, shaping the future of the automotive industry. Every year, over 150 million carats of diamonds are mined worldwide. But did you know that some mines are so deep that the temperature inside exceeds 110 degrees Fahrenheit, and powerful explosions can cause seismic tremors felt up to 50 miles away? Diamond mining isn't just digging. It's a full-scale scientific operation that starts with satellite analysis and can last for decades. How are these precious stones found? How do drilling rigs reach depths of 10,000 feet? And what happens to diamonds after they're mined? Let's break it down together. Diamonds form deep beneath the Earth's surface and are brought up through volcanic processes that create kimberlite pipes. These pipes, made of ancient igneous rock, are the primary sources of diamonds and can reach depths of over 10,000 feet, with temperatures inside the mines exceeding 110 degrees Fahrenheit. To cool these environments, powerful ventilation systems compress air. In some mines, the air is so pressurized that if a door between compartments is suddenly opened, the wind force can knock a person off their feet. Sounds dangerous, right? Before mining begins, geologists conduct extensive exploration that can last for decades. The process starts with analyzing satellite images and aerial photography. This is followed by field studies, where geologists collect rock samples for chemical analysis. Special attention is given to the presence of indicator minerals like garnets, ilmenite, and pyrope, which suggest the potential presence of diamonds. If the exploration yields positive results, detailed surveying begins. Drilling rigs create boreholes up to 10,000 feet deep, extracting core samples, cylindrical sections of rock. These samples undergo thorough laboratory analysis to assess the diamond content in the rock. Geophysical methods like magnetic surveys, electromagnetic scanning, and gravimetry are used. Open pit mining is employed when the deposit is relatively close to the surface. Underground mining is used if diamond-bearing rocks are located at significant depths. Mine shafts are constructed, allowing workers and equipment to descend. Mining begins with drilling boreholes into the kimberlite rock. For this, massive drilling rigs over 50 feet tall are used. Each borehole can reach lengths of 2,000 feet, and a single mine may have tens of thousands of such holes. After drilling, explosives are placed in the boreholes, and the detonation occurs under strictly controlled conditions. Some diamond mines use such powerful explosives that underground blasts can trigger minor seismic tremors detectable over 50 miles away. First, vertical shafts are dug, reaching depths of over 10,000 feet. The diameter of the main mine shafts often exceeds 20 feet. Additionally, horizontal tunnels are constructed, stretching for several miles. After the explosion, the rock in the mine breaks into pieces of various sizes, from large boulders to fine gravel. Powerful loaders with buckets lift the debris and transport it to central transfer points. Here, massive dump trucks, each capable of carrying over 250 tons of rock, load the extracted material and deliver it to the main tunnels. In some mines, instead of trucks, specialized electric trains running on tracks tens of miles long are used, capable of transporting over 500 tons of kimberlite rock per trip. The main tunnels are equipped with conveyor systems that start at depths of several thousand feet and extend to the surface. The length of these belt conveyors can exceed 15 miles, with belt widths over 6 feet. Some systems have multi-level structures, allowing simultaneous material transport from different parts of the mine. Before being placed on the conveyor, large rock fragments pass through crushing stations, where massive steel rollers over 20 feet long break the debris into fragments no larger than 3 feet in diameter. The crushers operate with compressive forces of tens of thousands of pounds per square inch and can process over 10,000 tons per hour. After initial crushing, the material is loaded onto the main conveyor belts, which transport it to the washing system. In some sections, the conveyors pass through special grottos equipped with giant sieves with holes of various sizes. During transport, smaller rock particles are sifted and directed to separate processing lines, while larger pieces move to the next stage of crushing. The newest mines are equipped with automated control systems that analyze the rock composition in real time and adjust conveyor speed and crushing intensity. As the future diamonds approach the surface, they are fed into special bunkers where the rock accumulates, ready for further processing. The capacity of these bunkers can exceed 100,000 tons, and their structure allows for even material distribution to washing and sorting facilities. In mines located in deep regions, transporting the rock can take several hours, with annual extraction volumes reaching millions of tons. When I was a kid, my family loved going to the beach. It didn't happen often, my dad rarely had time off, but when it did, everyone was thrilled and happy. Diving underwater to find seashells, crabs, or even clams, I never imagined that diamonds could be mined from the sea. Deep-sea diamond mining is one of the most complex and technologically advanced methods in the mining industry. Mines are located where kimberlite pipes or alluvial deposits lie beneath the ocean floor at depths exceeding 500 feet. Geologists begin by conducting surveys using underwater drilling rigs. These rigs are stationed on specialized offshore platforms or vessels equipped with computerized navigation systems for precise positioning over potential deposits. Once diamond-bearing deposits are confirmed, the construction of an underwater mine begins. This is a complex process involving the creation of sealed tunnels or the use of massive drilling capsules operating under high pressure. One method involves using giant seabed drilling complexes, which can exceed 200 feet in length and weigh over 5,000 tons. These complexes are equipped with diamond-tipped drills capable of cutting through even the hardest rock. During drilling, a specialized hydraulic system creates a water flow under pressures exceeding 3,000 pounds per square inch, washing out small rock particles and diamonds into special reservoirs. Another method uses giant underwater vacuum systems that can descend to depths of up to 1,000 feet and suck up hundreds of thousands of cubic feet of rock per hour. The material is then brought aboard a vessel or platform for initial processing. Special underwater crushers can process up to 50 tons of kimberlite rock per hour. Powerful pumping systems are used to transport the rock to the surface, capable of moving up to 1 million gallons of water per day. Streams of enriched rock are directed through pipelines that can stretch for several miles. The material then enters large sorting tanks, where it passes through gravity separators. Heavier diamonds settle at the bottom, while lighter particles are washed away and returned to the sea. Remotely operated underwater vehicles play a crucial role in deep-sea mining, operating at depths of up to 10,000 feet. They are equipped with manipulators that can precisely collect large diamonds directly from the seabed. Their high-resolution cameras allow operators, located hundreds of miles away, to control the process in real time. Deep-sea mining is so complex and costly that only a few countries in the world have the necessary technology. It can cost hundreds of millions of dollars, and the full mining cycle can take over 10 years. Despite the challenges, this method yields millions of carats of diamonds annually, supplying the global market with precious stones hidden in the ocean's depths for billions of years. On the surface, the extracted rock is crushed in processing plants, where massive steel jaws over 20 feet long break the stones into fragments smaller than 2 inches. Each plant can process over 10,000 tons of material per day. After crushing, the rock passes through a series of washing tanks filled with water and chemical reagents. Diamonds, which have high density, settle at the bottom, while lighter minerals are washed away. Once the material is on the surface, specialized X-ray separators are used to identify diamonds based on their ability to fluoresce under ultraviolet light. Magnetic separators work by exploiting differences in the magnetic properties of materials. Diamonds are non-magnetic, while most minerals in kimberlite rock have weak magnetic properties. In these systems, the rock is fed onto rotating drums over 20 feet long, which generate strong magnetic fields exceeding 10,000 Gauss. Magnetic mineral particles stick to the drum's surface and are removed into a separate container, while diamonds and non-magnetic rock residues move forward. X-ray systems are used in the next stage, when the rock is already significantly purified. These systems rely on diamonds' unique ability to fluoresce under X-ray radiation. The stones enter a special tunnel where they are exposed to X-rays with energies of up to 200 kiloelectronvolts. The diamonds begin to glow, and highly sensitive optical sensors instantly detect their location. The system then activates a high-speed air jet operating at pressures exceeding 100 pounds per square inch, which literally blows the diamonds out and directs them into a collection container. The cleaned diamonds are sorted by size, quality, and color. The sorting process is fully automated and managed by operators in specialized control centers. Each operator monitors dozens of X-ray systems using high-resolution computer panels. Modern systems use machine learning algorithms that can adjust equipment parameters in real time for maximum efficiency. If malfunctions or deviations occur, operators can manually change settings or redirect material flows for reprocessing. A single system can process up to 20 tons of material per hour with precision that detects even the tiniest diamonds smaller than 1/10 of an inch. At large diamond mines, dozens of such systems operate simultaneously, extracting hundreds of millions of carats annually. After sorting, the diamonds are sent for cutting, where artisans use lasers and mechanical tools to transform them into precious gemstones. Once cut, they enter the market, sold as part of jewelry or used for industrial purposes. Ever wondered where piles of old newspapers and boxes disappear? Every day, recycling centers process thousands of tons of paper waste, sorting it in seconds and transforming it into fresh sheets. Picture this: massive hangars, conveyor lines as long as a football field, sorting machines equipped with optical sensors, and drying cylinders heated to 260 degrees Fahrenheit. In just 5 to 7 cycles, paper fibers are reborn, becoming packaging, notebooks, or even furniture. Let's dive into the secrets of paper transformation. Think old newspapers or cardboard boxes are just trash? Think again. They have a future. It all starts simply. Paper and cardboard are collected. That includes old magazines, packing boxes, and even crumpled receipts. From there, the sorting begins, dividing materials by type and quality. For instance, cardboard is denser, while office paper is thin and clean. Sorting is a crucial step in giving paper a second life. So, let's break it down, step by step, in vivid detail. First, meet the key players in the process: machines and people. At large recycling centers, automated sorting lines handle the bulk of the work. But human hands are still essential. Operators on conveyor belts carefully check the paper's quality. It's a teamwork scenario where machines do the heavy lifting and people fine-tune the details. Recycling centers often look like giant hangars filled with mountains of raw material. Stacks of old newspapers, cardboard boxes, office documents, and even postcards. Here, conveyors roar and automated sorting systems buzz, processing everything. Here's how it works, step by step. First up, the initial inspection. Once collected, garbage trucks or special vehicles deliver the paper to the sorting center. At this stage, large contaminants like plastic wrappers, fabric scraps, or glossy-coated materials are removed by hand. Next, the automated machines take over, sorting paper by type and quality. Types include cardboard, newspapers, office paper, glossy paper, and packaging. Quality-wise, it's about separating clean paper from dirty, like sheets with grease stains or adhesive residue, which can't be recycled. Optical sensors and air filters play a big role here. Sensors scan the paper, while compressed air streams direct materials into their respective categories. Cardboard goes left, newspapers go right. Even the best machines make mistakes, right? That's where human operators step in to remove leftover foreign objects, like tape, staples, or plastic windows from envelopes. This process moves fast and demands sharp attention. After sorting, the paper is compacted into massive bales for easier transport to factories. Imagine blocks the size of a refrigerator, neatly packed and ready for a new life. Fun fact, old newspapers are easier to recycle than glossy magazines. Why? The glossy coating is harder to remove. Office paper, being high quality, often gets turned into new sheets for printing or even toilet paper. Next comes shredding and cleaning. the phase where old paper becomes the base for new material. Think of it as a paper bath, with powerful machines that not only shred, but also meticulously clean the paper of any impurities. Let's dive into the details. Compressed paper bales go into hydropulpers. Sounds intense, but these are just giant mixers. The paper is soaked in large amounts of warm water to help separate the fibers. Why water? It softens the paper, breaking it down into its cellulose fibers. Special chemicals, safe for the environment, are often added, like soap or alkaline solutions, to remove ink and glue. The hydropulpers kick into action, spinning water and paper at high speeds. The result? The paper breaks down into microscopic fibers, turning into pulp. Yes, that's the term. A gray, wet, slurry-like mass. At this stage, old boxes, newspapers, and letters lose their form and start a new cycle of life. The next step is cleaning the pulp to remove contaminants like plastic, glue, staples, and ink. It starts with screens of varying sizes. The pulp is pushed through under pressure, leaving larger debris like tape, staples, plastic bits, or thread behind. Smaller particles continue downstream. Then come the centrifuges. Remember physics class? In a centrifuge, everything spins, and heavier particles like sand or metal sink to the bottom, while lighter materials like plastic films rise to the top for separate removal. Water and centrifugal force work together, a perfect team. For ink removal, a process called de-inking is used. Foam made from soap and chemicals is added to the pulp. As the mixture spins, bubbles lift the ink to the surface, creating a frothy layer that carries the ink away. This method, called flotation, works like separating oil from water. Only here, it's ink instead of oil. Finally, the pulp is rinsed with clean water to remove any leftover chemicals or impurities, leaving a clean, fibrous mass ready for the next step, forming new paper. Let me know if you'd like further refinement or adjustments to the style. Glue, especially from labels or packaging, can be a real nuisance. During the cleaning process, it forms sticky clumps. To deal with this, special machines called tack removers capture those clumps before they ruin the final material. At this stage, the pulp is clean, light gray, or almost white, ready for the next step, forming new paper or cardboard. Old newspapers and boxes transform into material that can become packaging, napkins, or even part of furniture. Here's something fascinating. Paper can go through this recycling cycle 5 to 7 times before the fibers become too short for further processing. But until then, hooray, the paper's life continues. From the cleaned pulp, new sheets of paper or cardboard are created. The pulp is pressed, dried, and voila, a new product appears, the packaging for your favorite smoothie or a sleek notebook for your ideas. First, the pulp is spread into a thin, watery layer. It's poured onto a massive moving conveyor covered with a fine mesh, a sort of endless cloth that keeps moving. Water starts draining, and the pulp gradually thickens. This is where pressure takes the stage, turning the process into a true display of technical mastery. The first press, called the forming press, provides a gentle squeeze. Rollers press the pulp onto the moving mesh, evening out the thickness. These rollers are set at varying heights and pressures to make the pulp uniform. At this point, the pulp loses about half its water. Simply put, it goes from a watery mass to something resembling damp felt. Not yet paper, but with a clear structure. Next, the sheet moves to the second press, known as the smoothing press. Here, the pressure increases significantly. Heated rollers squeeze out the remaining water, speeding up the drying process. Not only does the paper or cardboard become thinner, but it also gains strength. At this stage, texture can be added. For instance, office paper gets a smooth finish, while packaging cardboard might have a more textured surface. This is achieved using rollers with patterned surfaces. After pressing, the sheet passes through a series of drying cylinders, massive metal drums heated from the inside. These cylinders reach temperatures of 260 degrees Fahrenheit, and the sheet glides over their surface. Moisture evaporates, leaving the paper or cardboard dry and strong. The cylinders press the sheet tightly against their hot surfaces, ensuring even and quick drying. Alongside the heat, hot air blowers are used to prevent uneven drying. After all, the paper needs to be consistently dry across its entire surface. During drying, the thickness of the final product can be controlled. For example, to make thin paper for notebooks or thick cardboard for boxes, adjustments are made to the roller pressure and the number of passes through the drying cylinders. Before the final drying stage, a special coating can be applied to the sheet, for instance, to give it a glossy finish. These coatings might include starch mixtures to strengthen the paper or clay solutions for added shine. The coating is applied in a smooth layer using yet another roller. After drying, the sheet becomes a finished product. But it doesn't end there. It can be rolled into giant reels if it's destined for printing houses or factories. Alternatively, it can be cut into individual sheets like office paper. Here's a cool fact. One of the main goals of this entire process is to preserve the cellulose fiber's properties as much as possible. These fibers give paper its strength and flexibility. In a way, each sheet is the result of a symphony of machines and human ingenuity. Recycled paper becomes the foundation for thousands of new products. In the packaging industry, it's used for delivery boxes, shopping bags, and disposable cups. It can even turn into furniture or decor, creative cardboard chairs, lamps, or even bookshelves. These items are stylish and can last for years. Most commonly, paper is recycled into stationery, notebooks, folders, and even paper pens. Recycled paper is also ideal for creative projects like greeting cards, scrapbooks, or home decorations. It's amazing to think how an ordinary newspaper or box can live a brand new life. Instead of ending up in a landfill, it gets a second chance to become something useful. Sell 100 million pairs of shoes in a year? What kind of production can pull that off? You won't believe it, but Crocs did just that. Today, we're gonna walk the path of the world's lightest footwear, from a polymer bead to a cult favorite. And from that cult, we'll move on to recycling these shoes. Crocs was founded in 2002, and their products instantly took over the world. The manufacturing process of Crocs is pretty complex. It all starts with the raw materials. They're the key to Crocs' success. The material they're made of is called Croslite, a patented foam resin that provides lightness, comfort, and durability. It's not just rubber shoes like many people think, but a special closed-cell foam material. Croslite is a type of ethylene vinyl acetate, a polymer material that boasts water resistance, cushioning properties, and high wear resistance. Polymers for Croslite are produced from oil or natural gas, which are processed into polyethylene. Large chemical enterprises located in Asia, Europe, and the USA supply this raw material to Crocs factories. The raw material is transported in the form of pellets. They're easily shipped in large containers and stored in dry conditions until production begins. The main Crocs manufacturing factories are located in Asia, Vietnam, China, and Indonesia. These countries have access to affordable labor, large volumes of raw materials, and robust logistics. The name Crocs comes from the word crocodile, because these animals can live both in water and on land, just like these shoes. Now, let's head over to the production line, bro. Check out how these guys load the pellets into a special machine where they're heated to high temperatures. It's seriously hot. The melting temperature of the material reaches 400 degrees Fahrenheit. The material melts and becomes liquid, resembling thick cream. The liquid polymer is poured into special molds that shape the shoes. The molds are subjected to high pressure, ensuring all the details are filled tightly. Excess polymer oozes out under pressure from the mold, kinda like creme brulee. If it weren't for the smell in the factory, you'd be tempted to take a bite, right? But it's definitely not something edible. As it cools down, the material expands, creating Croslite's unique closed-cell foam structure. This provides lightness, elasticity and softness, water resistance, and antibacterial properties. The shoes weigh on average only about 5 to 7 ounces. Confess it, who's gonna run off to weigh their Crocs after watching this video? But let's keep going, bro. Shoes made from these amazing pellets don't absorb odors and are easy to clean. But all this happens after they're taken out of the mold. That's when the excess material is trimmed off and the edges are smoothed. Look how quickly and precisely these guys work. The surface is polished to avoid burrs or roughness. It takes less than 5 minutes to produce one pair of Crocs. After trimming the excess material from the mold, the cut edges are treated with grinding machines. This is done to remove sharp edges, burrs, or irregularities left after trimming. First, they use abrasive belts or discs with medium grit, which quickly remove large irregularities. Rotating grinding tools allow the edges to be processed evenly and replicate the shape of the sole and the upper part of the Croc. Then, the workers move on to fine polishing. To ensure the surface is soft and smooth, they use fine grit abrasives like sanding sponges. This stage removes microscopic roughness that could cause discomfort when wearing. For particularly sensitive areas, like the edges of the ventilation holes, they use hand tools, like sanding sponges or polishing pads. Hand polishing guarantees the absence of even the smallest burrs. In the US, the military uses them as shower shoes because they're water-resistant and dry quickly. Other elements are added to the finished shoes, namely straps and gibbets. The straps for securing are attached separately. They're made from the same material or from more rigid polymers. Rivets are installed on the straps, allowing them to move. What kind of gibbets do you have, bro? Gibbets are decorative accessories that attach to the ventilation holes of Crocs. They allow you to personalize your shoes by adding elements that reflect your individuality, hobbies, or even mood. The idea for decorating Crocs came about in 2005. It was invented by Sherry Shubitsky, a mom who, together with her kids, came up with a way to adorn Crocs with tiny plastic charms. Let's all write in the comments, "Thank you, Sherry." Sherry used regular decorative buttons that her kids attached to the ventilation holes on their Crocs. The idea was so popular among friends and acquaintances that it eventually turned into a full-fledged business. In 2006, the Crocs brand bought the idea for $10 million, adding gibbets to their official product lineup. Gibbets are small decorative elements made from soft plastic or silicone. They have unique shapes and a special fastening mechanism. Gibbets can be in the form of symbols, emojis, logos, favorite movie characters, animals, plants, inscriptions, and so on. The back of the gibbets has a small stem or pin that fits into the ventilation hole of the Crocs. Thanks to the material's elasticity, the gibbets easily inserts and holds very securely. First, designers create sketches of future charms. These can be popular symbols, current memes, or seasonal themes. For example, snowmen in winter or sunflowers in summer. After the design is approved, three-dimensional models are created, which are used to form production molds. Liquid plastic or silicone is poured into molds with detailed designs. After cooling, the material solidifies, retaining the shape of the charm. Simultaneously, the back fastening part is formed, ensuring a secure connection with the Crocs. In 2021, a unique gibbets was sold at auction for $10,000. It was made of gold and adorned with diamonds. As for coloring and applying patterns, various techniques are used here, as you can see. Color is added at the stage of melting the pellets so that the color is evenly distributed throughout the structure. And to create print, they use laser engraving or printing techniques. Each pair undergoes quality checks for compliance with shape, color, and absence of defects. If defects are found, such pairs are discarded or sent for recycling. And that's the end of the production cycle. The finished Crocs are packed into boxes and transported by sea containers or by air to warehouses around the world. Crocs are comfortable shoes, but they present an environmental challenge. The Croslite material isn't a traditional plastic. At the same time, the Crocs brand is making efforts to make its products more eco-friendly and to find effective ways to reuse old shoes. The patented foam material doesn't decompose naturally, so if you throw out old Crocs, they can remain in landfills for decades. Croslite doesn't lend itself to standard plastic recycling methods due to its unique chemical structure. Recycling requires special technologies that most waste processing facilities don't have. You get it, bro. They invented a unique, durable material. But now, the problem is what to do with it afterward. In the past, Crocs implemented a program to collect old Crocs. They disinfected, refurbished, and passed them on to people in developing countries. So, we're cluttering up not our own country, but those who don't have a choice. Controversial idea, huh? That's why the program was discontinued, but it inspired the creation of new eco-initiatives. In some Crocs stores, you can leave your old shoes, which are sent for research into reuse or for conversion into energy resources. Today, old Crocs are sometimes used to obtain energy through the process of pyrolysis. Crosslight is burned in special furnaces, and the energy obtained is used for heat or electricity production. Admit it, that's a pretty good look. Also, after shredding, old Crocs can serve as the basis for new materials, such as rubber coatings for playgrounds, insulation material, or as construction or decorative elements.